Now the core of chapter 5, the routing algorithms, or the routing protocols. So a good routing protocol there should be able to identify good paths or good routes from the sending host to the receiving host through this network of interconnected routers in the middle. So that is essentially trying to come up with a path. Okay? A path is a sequence of routers, one connected to another, and connecting the initial source to the final destination, okay, such that this path here is the least in cost, so we pay the least, or the delay is the shortest, or the promised bandwidth there is the highest, therefore the congestion level will be the lowest. Okay, so finding a good path, that is the goal of a good routing protocol or routing algorithm. It's also one of the top 10 problems in computer network, just like reliable data transfer, just like congestion control. In the next couple slides, Polly is going to introduce this new term called graph. A network, okay, of routers interconnected by links is a graph. So let's focus on the network in the middle here. What you see is that we have router U, router V, W, X, Y, Z. So we have a set of routers, okay, and there are 6 of them. Now, between the routers, we have also links. So link UV here connects router U and router V. Similarly, UX here connects router U and router X. VX, V here, X here. VX is the link connecting router V and router X. Link VW, connecting router V and router W. So you see we can go over all the links defined here, and this forms the set of links interconnecting the routers. And coincidentally, a graph is also defined in a very, very similar way. A graph consists of the set of nodes and the set of edges interconnecting the nodes. So N here stands for nodes, and here E here stands for edge. So if you consider the routers being nodes, so the set of router here is the N here. If you consider links being the edges, then E here is the set of the edges. With the set of nodes, set of edges interconnecting the nodes, we do have a graph. So a network here is also a graph. And such an abstraction is really, really convenient later on when we're introducing the algorithm. It could also be useful when we're talking about other kinds of networks. So for example, in the application layer, chapter 2, for P2P, okay, you see there, there are peers here, there, all around the internet. And we establish connections between the peers, right? So we could do what? P2P communication. So if you consider each of these peers as a node, and these TCP connections or UDP connections connecting the peers as an edge, there, you also have a graph. You also have a P2P network. And you can also run a routing algorithm, okay, on a P2P network, if you think about it. And now we can talk about this other thing, okay, it's called the link cost. So associated with each link, okay, on a graph like this, you see a number nearby, that is the link cost. To denote the cost of a link connecting router X to X prime, we use this notation, CXX prime. So C WZ, connecting router W to router Z. The link here, the cost of that link is 5. Right? That cost, can be set in a variety of ways. For example, set it as the inverse of the bandwidth available. You can also set it to the inverse of the traffic level. You could also set it simply to a constant, such as, 1. Every link costs the same. 1. Okay. So that is link cost. Now the cost of a path, is essentially also very simple. From the source X 1 to the destination xp is the sum, okay, of all the link costs connecting from the source to each of the routers along the path, all the way till the destination. So it's the sum of the costs from the source to the first hub router, x2, c, x1, x2, plus c, the first router to the second router, x2, x3, and so on and so forth until the last router, xp minus 1, to the final destination. Okay. So let me use an example. Let's say traversing from U to Z, and we take this path. Yeah. The cost of the path will then be adding 2 to 3 to 5, and that will be 10 here. All right. So the goal of routing algorithm is essentially to find the least cost path, okay, between a pair of nodes, okay, from source to destination. In Poly, we'll be introducing 2 routing algorithms next. First is called the link state algorithm, second, distance vector. The link state routing works this way. Inside the network, each router, okay, in the router, it implements an algorithm. Before this algorithm can be triggered, the router needs to wait to have the complete topology and link cost information. What I meant by complete topology is this. Each router will need to know N, the set of routers composing the network. E, the set of links interconnecting all these routers in the network. And link costs of all the links, okay, connecting the routers in the network. So each router needs to know how the network looks like globally before the routing algorithm can be triggered. Another characteristic is this. The link state routing algorithm will run in just one pass. So provided global information of the network, trigger routing, route computes, and completes. As a result, each router not only knows the best route to all possible destinations, it actually knows, okay, all the best routes from arbitrary source in the network to arbitrary destination in the network. So the router there, very informative, knows how the network is like entirely and knows all the paths, okay, for all the possible destinations and source pairs. On the contrary, in distance vector, the routers no longer require global information. The routers also do not do one-pass route computation. Rather, the router only needs local information, namely, a router only needs to know how it's physically connected to the immediate neighboring routers and the link cost to the neighboring routers. And that's all. The route computation begins. With very minimum information, the computation gives you suboptimum results. Okay, so each router there, after running the distance vector algorithm, will know just slightly better than, nothing. And that information is definitely not quite good enough to give us the least cost paths. So what distance vector routing does is there. Each router will then, after some initial computation, exchange the result of the computation to the neighboring routers. Neighboring routers would also exchange what they know slightly better to the router here. Now, this router in the middle, after receiving slightly better information from the neighboring routers, can recompute and see if even better paths have been discovered. Okay, so if the router again discover better paths, then tell the good news to the neighbors. Similarly, neighbors would also tell slightly more information to the router. Okay, as such exchange expand, gradually traveling through the network. Okay, all the routers in the end learned about converge to the least cost path. Okay, so the process you see, computation, exchange, computation again, exchange again, computation yet again, exchange yet again. So the process is very iterative. It's going to take some time, but eventually, as the information propagates through the network, okay, everyone converges to the least cost path. Okay, so a very different model of doing route computation. Okay, link state routing being global, distance vector routing being local. Now, another way of classifying the routing algorithms is this. Okay, by judging at how the routes, okay, are being updated. Static routing is not updating the routes. Okay, so this is only for the network that is not changing frequently. Okay, and we know that this kind of network doesn't really exist these days. So all the routing algorithms that we're introducing are working this way. Okay, dynamic. That is also saying that routes can change. Okay, link costs can change. Okay, routers could suddenly be dead and then or suddenly being booted up. Okay, so we'll try to update these routes, repeat the computation, okay, periodically, or okay, in case we detect there's a link cost change or no change, okay, or some other changes.